Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. A channel section is said to be most economical or efficient section when it can pass maximum discharge for a given cross-sectional area and reference coefficient and bottom slope. So discharge equation that is equal to Q equal to AV. So for a given cross-sectional area of the channel, the discharge is maximum when V, that is flow velocity, is maximum. So equations available for the computation of uniform flow velocity is Manning's equation, that is V equal to 1 by n r raised to 2/3 and s naught raised to half, and other equation is Chezy's equation, that is V equal to c into root of r into s naught. For a given channel of non-roughness and bottom slope, velocity is maximum when hydraulic radius is maximum. R is maximum or R which is equal to A by P, that is maximum. Or we can say that P is minimum. So that means a channel section is said to be most economical or hydraulically efficient when wetted perimeter P is minimum. Now let me discuss the most economical or efficient section of the circular section. So the figure shows a circular channel with the flow depth y and radius r. Theta is the angle subtended by the water surface PQ at the center. In circular channel, unlike other channel sections, the shape of the flow area changes when the flow depth changes. Due to the change in shape of the flow area with the depth, the maximum mean flow velocity condition may not be the same as the maximum discharge condition. Hence, two separate conditions may be derived for the circular section. The flow depth y, that is equal to OS minus this distance. So this distance is r cos theta by 2 and OS equal to r. So r minus r cos theta by 2, that is equal to the flow depth y. So first of all, we can derive the condition of maximum discharge. So the flow area, so that means this shaded area, that is equal to area of the sector OPSQO minus area of the triangle OPQ. So area of the sector, that is equal to pi r square, that is the area of the circle, into theta divided by 2 pi, minus area of this triangle OPQ equal to half BH, so half into this length equal to r sin theta by 2. So the total length PQ, that is equal to 2r sin theta by 2 into this length equal to r cos theta by 2. So it becomes r square into pi get cancelled. So r square in theta by 2 minus these 2 get cancelled. So it becomes r square into sin theta by 2 into cos theta by 2. So if you are taking r square by 2 outside, then it becomes r square by 2 into theta minus 2 sin theta by 2 cos theta by 2, or A equal to r square by 2 into theta minus sin theta. Then wetted perimeter, that is PSQ, that is equal to r theta. So the discharge Q, that is equal to A into V, that is equal to A into C into root of R into S naught, that is equal to A into C into this R is replaced by A by P into S naught. So if you are taking A into this root, then it becomes C into root of AQ by P into root of S naught. So for the condition of maximum discharge, you have to differentiate this expression with respect to theta and equate into 0. For maximum discharge condition, AQ by P is maximum or differential of root of AQ by P with respect to theta, that is equal to 0. So if you are differentiating this term with respect to theta, then it is P into 3a square into dA by d theta minus A cube into dP by d theta divided by P square equal to 0. So dA by d theta, that is equal to r square by 2 into 1 minus cos theta and dp by d theta, that is equal to r. So if you are substituting this in this expression, then it becomes 3 by 2 r cube theta into 1 minus cos theta minus r cube by 2 into theta minus sin theta equal to 0, or the value of theta for the maximum discharge condition is theta equal to 308 degree, and the flow depth y, that is equal to y equal to r minus r cos theta by 2. So if you are substituting the value of theta, you will get the condition for maximum discharge, the value of y equal to 0.95 d, and hydraulic radius r, that is equal to a by p, a equal to r square by 2 into theta minus sin theta, and p equal to r theta. So if you are substituting the value of theta equal to 308 degree, then hydraulic radius r equal to 0.29 d. So for a circular channel, the most economical or efficient section for the condition of maximum discharge is theta equal to 308 degree or y equal to 0.95 d. Now let us discuss about the condition of maximum velocity of flow. The equation for the velocity, that is v equal to c into root of r into s naught, or v equal to c into a by p into s naught, where a by p is r. So velocity is maximum when a by p is maximum, or differential of a by p with respect to theta equal to 0. If you are differentiating this term with respect to theta, it is p into dA by d theta minus a into dp by d theta by p square equal to 0. So if you are replacing this dA by d theta and dp by d theta by means of these two expressions and substitute for p and a, then this equation becomes theta into r cube by 2 into theta minus cos theta minus r cube by 2 into theta minus sin theta equal to 0, or theta equal to tan theta, or theta equal to 257.5 degree. Now you can calculate the value of y for this maximum velocity condition as y equal to r minus r cos theta by 2 equal to 0.81 d, and correspondingly hydraulic radius r equal to a by p, that is r square by 2 into theta minus sin theta by r theta. Substitute for theta, then hydraulic radius r equal to 0.3 d. So remember, whenever we have to multiply it with theta, please don't forget to convert that into radian. Now we are going to discuss about two concepts related to the uniform flow. The first one is conveyance. For a constant cross-section area, so discharge equation, that is equal to q equal to a into v. So v equal to c into root of r into s naught if you are using Chezy's equation. So the discharge equation can be written as q equal to a c into root of r into s naught, or it can be written as k into root of s naught. K is called conveyance, which is a measure of carrying capacity of the channel. So this can also be written as k equal to q divided by root of s naught, or k equal to a into c into root of r. If you are using Manning's equation, then q can be written as q equal to a into 1 by n r raised to 2/3 into s naught raised to half, or it can be written as k into root of s naught. K equal to 1 by n a r raised to 2/3. So in uniform flow conditions, if the discharge and bed slope are available, then you can calculate k by using this equation, q divided by root of s naught. If channel geometry and reference is given, so you can calculate k as k equal to a c into root r, or k equal to 1 by n a r raised to 2/3. So conveyance is a measure of carrying capacity of the channel in uniform flow condition. Another concept is section factor. So Manning's equation is very commonly used equation. So the discharge equation can be written as q equal to a into 1 by n r raised to 2/3 into s naught raised to half, or we can express the conveyance k as 1 by n a r raised to 2/3, or represents k as q divided by root of s naught. So as we have discussed earlier, if discharge and bed slope is given, then we can calculate the conveyance using this expression. Or if the channel roughness and geometric variables are available, then we can calculate the conveyance based on this expression. If we are connecting this expression, then 1 by n AR raised to 2/3, that is equal to Q divided by root of S naught. Or we can rewrite this expression as AR raised to 2/3 equal to NQ divided by root of S naught. This AR raised to 2/3, that is called section factor for uniform flow computation. So AR raised to 2/3 represents vectored geometric variables, or this can be written as the function of y. So we can say that in uniform flow conditions for a given discharge and roughness condition and bed slope, there is only one depth is possible. That depth is called normal depth. Similarly, for a given roughness, bed slope and flow depth y, there is only one discharge is possible, that is called normal discharge. Similarly, for a given n, q and y, there is only one slope is possible, that is called normal slope or Sn. AR raised to 2/3 represents geometry of the wetted area. So this equation AR raised to 2/3 equal to NQ by root of S naught is very useful for the analysis and computation of uniform flow. So correspondingly, we can find out normal depth by n if NQ S naught is available, or we can compute the normal uniform flow discharge Qn if n by S naught is available, or we can compute normal slope Sn if NQ y are available. For computing normal depth yn, normal discharge qn and normal slope Sn, the basic equation is AR raised to 2/3, that is equal to NQ divided by root of S naught. Now the session comes to an end. For the time being it is enough. In the next class we are discussing about the flow measurement in open channels. Thank you for your patient listening. Please don't forget to press the bell button to get the notification of next video. See you, your SumamMiss.